contradiction. Contradiction. Okay, let me tell you about contradictions. Here are examples of contradictions. 1 equals 2. Nonsense. Contradiction. So contradiction is nonsense. Okay. Here's another contradiction. N squared is bigger than n. N squared is less than n, where n is, let's say, a natural number. Okay. So n is a natural number. Okay. This could be true depending on what n is. So if n is a natural number, this is nonsense, not possible. False. Okay. The absolute value of x is less than x. Never possible. Okay, not for the real numbers. X is greater or equal to 1 and x is less than 1. Nonsense. It's not possible for x to be both greater or equal to 1 and less than 1. Now, this is the typical type of contradiction. If you think of this as a statement P, then this is exactly the statement not P. And so what I'm claiming here is P and not P. That's the prototype contradiction, where you claim something and you also claim its negation. Nonsense. It can never be true. So these are examples of contradictions. I'll call them fishy. They smell bad. Okay, contradictions. Fishy. Okay. Now, fun fact. Mathematics is what we like to think it's consistent. Okay? So what that means is we built an axiomatic system, which we call mathematics, in which you can only prove true things. Okay? So that's a fundamental sort of goal when you build a consistent mathematics, and our mathematics is consistent, so you can only prove true things. Okay? So now let's say you're deriving something, you're going along and blah, 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 and now you end up at proving something that's not true, something that's a contradiction. Okay? So you've ended up at something fishy. Okay? Now, since in mathematics you cannot prove fishy things, you cannot prove false things, it means something is wrong in your derivation. So that leads us to the principle of contradiction. So the principle of contradiction. So if you derive something fishy, if you derive something, and I'm going to put it in red, fishy, then you can immediately conclude there's something wrong in your derivation. At least one of the steps in your derivation is wrong. And then at least one step in your derivation is wrong. And that seems kind of obvious, right? If you derive something wrong, if you derive something fishy, then somewhere along the line you have made a mistake. Now, this principle of contradiction might seem self-evident, but be careful. Once you give me this principle, it's going to provide for me a very general, very powerful, but also very dangerous method of proof. So, let me show you this proof. So once you give me this principle, it's given me this very powerful, general, dangerous method of proof. Let me show you this method of proof in action. So let's prove some things. So, theorem. And here's the general way in which a proof by contradiction works. Theorem. The square root of 2 is not in the set of rational numbers. So that's the mathematical way of saying the square root of 2 is not rational. So here's the way a proof by contradiction starts. And this is why it is so absolutely general. You can use it to prove anything. So I want to prove this, and I don't know how to prove it. Okay? So the method of contradiction says, well, in that case, try contradiction. So here's how contradiction works. You want to prove this? Well, go into a world in which this is false. Okay? Just like we were proving an implication. So go into a world where this is false. So step 1, for anything you're trying to prove, go into a world where the theorem is false, or the result, whatever it is. So if this is false, that means that, the square root of 2 is a rational number. Okay, now let's do stuff in this world. Okay, so let's explore this world. That's the next step. Explore this world. Well, in this world where square root of 2 is rational, what does that mean? So in this world, if we're exploring, it means that, square root of 2 is, A star over B star. And this is, we discussed this last time, and this is known as putting a fraction in its lowest terms when you took high school algebra, okay, where, this fraction is in its lowest terms. If it's rational, you can write it as a fraction in its lowest terms. And we proved this before using the well-ordering principle, where A star and B star have no common factor bigger than 1. Okay? And now I'll go through the argument quickly. So we're still exploring. We're just doing random mathematical manipulation. It's just that because I know where I'm going, my exploration is quite direct. But in general, in a proof by contradiction, your exploration can meander a little bit. And what's the goal? Yeah, I'll show you what the goal is in this exploration. So this means that A star is equal to square root of 2B star squared, to B star. That is, if I square both sides, A star squared equals 2B star squared, because the square root of 2 squared by definition is 2. Okay? And this means that A star squared is even, so A star is even. Remember we proved this before. Any even square came from an even number. If A star is even, this means that A star is equal to twice some other integer. So plugging twice k into here, this means that, 2k is equal to square root of 2b star, squaring both sides. So 4k squared equals 2b star squared. Dividing both sides by 2, we get that b star squared, which tells us that b star squared is equal to 2k squared. Or b star is even. B star squared is even. And if a square is even, it means that the number itself must be even. So b star is even. Okay, so now we've explored and done such and such and such, we've come up to a point where we've observed that A star is even and B star is even. So, A star is even and B star is even. That is, they have a common factor 2. They have a common factor 2. And I'm going to underline this. Okay. And I claim that we have a prototype fishy situation where I've said something and then I've said something that directly contradicts that. So what did I say? First, A star and B star have no factor bigger than 1. And now I've meandered in this world, I've explored, and I've discovered that A star and B star have a common factor 2, which directly contradicts that. And this is fishy. And now we go back to the principle of contradiction, which says that, the moment you have derived something fishy, and that was the goal of the exploring. And you might ask, well, how did I know to explore this way and that way? Well, that's the creative, difficult part in a proof by contradiction. Okay? But the goal of the exploration, the goal of the mathematical derivations is to get to a situation where you clearly have something fishy. And sometimes you have to argue, you have to show why is it fishy. In this case, it's kind of obvious why it's fishy. Okay? And once you get to something fishy, now we invoke the principle of contradiction, which says that the moment I have derived something fishy, something is wrong. Okay? So let's go and look at all of our steps. Well, 5 clearly follows from 2, okay, because from 2 and 4, because, from 3 and 4, where here we say A star is even, here we say B star is even, so therefore they have a common factor 2. And this step 2 is a direct consequence of the well-ordering principle. So if you say that this step was wrong, you have to give up the well-ordering principle, which is an axiom. Okay, if you say, and then once we have this, all of this is basic algebra, so all of this is correct. All of this is correct. So that's very important. that my explorations, my mathematical derivations have to be correct. So, but something has to be wrong in this proof. That's the principle of contradiction. And what could it be? Well, the only thing that could be wrong is this first step. Go into a world where the theorem is false. It must be wrong. In other words, there must not be a world in which the theorem is false. And if there cannot be a world in which the theorem is false, then it means that the theorem is true. So this is the flawed step in this derivation. So this is flawed. Okay. And if that's the flawed step, then you cannot go into such a world, in which case every world has this theorem true. Okay. Now, let me summarize this proof mechanics. Okay. And that concludes the proof of the theorem. Let me summarize the proof mechanics. Basically what I did is I assumed the theorem is false. And so you can do this with anything. That's why it's so general and so powerful. Okay. So I assume theorem false. Now I explore, which means do valid mathematical derivations until you get to something fishy. So this has to be valid. The moment you have obtained something fishy, and since everything here is valid, it must be that the theorem is true. So you're not allowed to assume it's false. Okay? That's the mechanics of the proof by contradiction. That's why it's also dangerous, because it's very easy to make a small mistake in your explorations, and whenever you make a mistake, you might come to something fishy, and at that point, the reason you came to something fishy is because of the mistake, but you mistakenly think that the theorem is true. So you have to be very careful in a proof by contradiction. This is sort of a very indirect method of proof. It's sort of like, you give the whole game away. You give up the whole theorem. You assume it's false. You give up the whole theorem, and then you wander around, and then you take it back. Okay? Because you wandered into something fishy, something that's not possible. It's kind of like the ultimate chess sacrifice. I sacrifice the theorem, and then through showing that sacrificing the theorem results in nonsense, I get the theorem back. The ultimate sacrifice in chess. Okay. So that's contradiction. Let's do another example. And you can try to solve this problem before me. Okay? So, prove that no matter how you choose A and B as integers, it's not possible to get a situation where A squared minus 4B is equal to 2. So you can try to find integers for which this is true. I'm claiming it's not possible. So A squared minus B minus 4B is never equal to 2. So it's not equal to 2. So you try to prove it while I erase. Okay, so if you proved it, phenomenal. If you didn't, I'm claiming that contradiction is a great way to prove this. And so let's see how that works. So immediately, so general, we immediately assume that it's possible. So just like we assume that square root of 2 can be represented as A over B, let's assume that we can find A and B for which this equality holds. Okay. So A squared minus 4B equals 2. Assume for some A and B. Okay, assume it. Well, we're assuming it. Okay. And that's the first step in a contradiction proof. Now we're going to wander around. Well, let's wander around. So what this means is that A squared is equal to 2 plus 4B. Okay. And I just took this to there. I'm wandering around. And what I observe here, this is even. So this is even. So A is even, because it equals an even number. And we know that if A is even, then A squared is even. And we know that if A squared is even, then A is even. Because every even square came from an even number. So A equals 2k. So 2k squared is equal to 4 plus, is equal to 2 plus 4b. Okay, so 4k squared is equal to 2 plus 4b. Divide both sides by 2. 2k squared is equal to 2b plus 1. Oh, I'm getting ready to puke. Okay, because I claim that here is something very, very fishy. Okay, and now why is it fishy? Because look, on this side is a multiple of 2. 2 times something. So this is even. On this side is a multiple of 2 plus 1. So this is odd. How is it possible for an even number to equal an odd number? Very, very fishy. And that's the end of my proof. The moment my exploration of this fictitious world where I assume the theorem is false, where I assume the claim is false, the moment I come to something fishy, I have immediately proved that this fishy world cannot exist, because you're not allowed to derive wrong, fishy things. So if this world cannot exist, it means that this is not possible. It means that the theorem is proved by contradiction. What a beautiful proof technique. Okay, now let me end the discussion of proofs by talking about proofs involving sets, and then I'll give you some, rules of thumb for. So now we've seen many different types of proofs. You might be wondering, well, we've seen so many different types of proof. How do I know which kind of proof to pick when? So let's quickly talk about sets, and then I'll give you some tips for picking a proof template.